Well, ladies and gentlemen, it's an enormous pleasure to be here, and a huge thank you to Catherine and her team for organizing this, but a huge thank you to you for being here. The commitment of time to continuing education is essential for good patient and client care, and by being here you're exhibiting that, so thank you very much. I'm going to talk to you about this system here, the Healite 2, and I believe that it is a new concept in phototherapy, and I hope by the end of my presentation I will have shown you why it's a new concept in phototherapy. In the beginning there was nothing. And God said, "Let there be light." And there was light. Now, when we look at this word light and we take it back down to the first letter, it's very important because we find this letter L, light, in LEDs. We find it in laser, which of course, as you know, stands for light amplification by stimulated emission of radiation. And we find it in IPL, intense pulsed light. So the thing that holds all of these systems together is this energy which we know as light. And because they all depend on light, they must all obey the laws which govern light. So I'm going to start by taking you through, very briefly, the physical properties of light. Light is actually a form of energy, and a beam of light is made up of millions and millions of tiny little packets called photons. The word photon comes from the Greek word meaning light. And photons have their own energy. They are weightless packets of pure energy. And when this energy interacts with our tissue, we get some kind of reaction. And we can control that reaction by depending on what sort of photons we are using and how many of them we are delivering to the tissue. Light interacts with the skin in four main ways. First of all, it is reflected off the stratum corneum. Secondly, it can be transmitted through the epidermis and dermis. It can be scattered by the turbid media of the skin, which is made up of so many disparate optical characteristics, so that one small beam can involve a very large area of tissue. And finally, light can be absorbed in the tissue. And this is the most important of all because this is the direct energy exchange, when the energy from the photon is transferred to the tissue via cells. And the first law of photobiology makes clear why this is important, because without absorption you can have no reaction. And this involves two aspects. First of all, we have to match the light to the target, and secondly, we have to have enough light so that we reach the target. So if we consider this little model here with two targets in the dermis, the light is matched to the target, so we get a reaction. But when the light is not matched to the target, we get no reaction because it's not been absorbed. Now, if we take these same targets and place them deeper in the dermis and we use the same light, we find no reaction because there's not enough oomph to the light to get it down to the target. So if we add that intensity, we reach the target, there's absorption, and we get a reaction. And there's only one aspect of light that determines both target specificity, or chromophore, and also the depth to which the light will inherently penetrate into tissue. And you might think, aha, that's the output power. No. The most important factor is the wavelength or color of the light. And particularly in phototherapy, wavelength is of critical importance. This is the wide light spectrum, which involves a number of lasers, and we have ultraviolet going into visible and then going into near and mid-infrared. And wavelength is measured in nanometers, which is 1 billionth of a meter. We have a number of lasers, just to show you where they are on this spectrum. The excimer, which is used in ophthalmology, the argon, which was a real stalwart in dermatology and ophthalmology, the dye laser, which is still used, the ruby, the neodymium YAG, erbium YAG, and the good old carbon dioxide. And then we have IPL. IPL is not a laser, it's a polychromatic light source, and it can span from the near infrared into visible blue-green. And then we have the three wavelengths offered with the Healite: 415 nanometers, which is visible blue, 633 nanometers, which is visible red, and 830 nanometers, which is near infrared. And each of these wavelengths has a specific target or targets and can be used to do certain things. And as we go through the presentation, you'll learn what these things are. Light penetrates into our skin. In fact, light can penetrate through tissue. And I'm going to show you here a photospectrogram. Here we have wavelength across the bottom from 500, which is blue-green, and 1000 nanometers or 1010 in the near infrared. And on the y-axis, we have the optical density of the tissue. And OD, the higher the OD, the poorer the penetration of the light. So this is a photospectrogram of light through a human hand in vivo, where the generator is placed above the hand and the receptor is placed below the hand. And this is what the curve looks like. You can see that for the shorter visible wavelengths, penetration is extremely poor because absorption is extremely high. You only move 43 nanometers, 43 billionths of a meter, and you find that penetration increases by 3.5 orders of magnitude. That means over 10,000 times better penetration. And the deepest penetrating wavelength is 830 in the near infrared, because it's not absorbed in blood, it's poorly absorbed in melanin, and it's right at the bottom of the water absorption curve. So these are important when you consider targets in tissue. Where is your target? What wavelength should you use to reach that target? And this tells you that if the target is in the dermis, any of the shorter wavelengths of blue, green, yellow will not penetrate deeply enough to affect any cells in the dermis, but they will affect cells in the epidermis. Red and infrared, on the other hand, can reach into the dermis and down into the subdermal layer. All right. Now we have a question I can answer you. When you see this question mark, it means that I don't know what I'm going to say next. No, it means that I might not know what I'm going to say next. I'll answer this gentleman's question quickly. What is the difference between an LED and a laser diode, or a laser? The LED, the good LEDs, are what are called quasi-monochromatic. Quasi meaning almost, or quasi-monochromatic, whereas lasers are monochromatic. And I'll explain this, I think, in the next section. In phototherapy, we have a direct cell transfer of low incident levels of photon energy from the photons directly into the cells. This raises the energy level of the cell, but without heat and without damage. But we do achieve a viable clinical effect. This is also known as low-level light therapy, or LLLT, which used to be low-level laser therapy, but now LEDs are in the picture, it's low-level light therapy. And we compare that with photosurgery, which deliberately creates heat and damage to achieve its surgical effect. When we take a cell and we look at the cell damage threshold and we start pumping light energy in the form of photons into that cell, we get a level of reaction that increases in proportion to the stimulus. And as long as that stimulus reaches the cell damage threshold and doesn't go beyond, the cell is activated, and that's LLLT. But if we go beyond that, first of all, we will damage the cell, and then, if there's enough light, we will kill the cell, and that's photosurgery. So it's this side of the cell damage threshold that we're going to be looking at this afternoon. So why should we use light-emitting diodes when we have other light sources? Well, if you'd asked me this question 15 or 20 years ago, I would be rolling on the floor laughing. Because light-emitting diodes in clinical application 15 years ago were a joke. They were being used, and some are still being used that shouldn't be used, but they were a joke. They still have an effect, but you might as well get the same effect standing in front of your Christmas tree. Or indeed, traffic signals. So the old LEDs had a huge angle of divergence, which means the photon intensity was extremely low. The output powers were very unstable, and on their plus side, they were very cheap and cheerful. However, this all changed when we could get a red LED. We could not get a 633 nanometer red LED. And this changed in 1998 with Harry Whelan, Professor Harry Whelan and his colleagues working in NASA, National Aeronautic Space Administration Space Medical Laboratory. And they developed the NASA LED, and this burst onto the phototherapy scene as a new source, giving energy which was many orders of magnitude. In fact, it was more than 100,000 times more powerful than existing LEDs. The output power was stable and consistent, and the wavelength was quasi-monochromatic. This means that you have a rated wavelength with a few nanometers either side. So it is quite possible now to have a red LED at 633 nanometers plus or minus a couple of nanometers. That's in the good quality LEDs. In the poor quality LEDs that you tend to find in the cheaper machines, you'll find it's 633 nanometers plus or minus 20 to 50 nanometers. So it's no longer 633 nanometers. You know, it's a mixture of red. What are the advantages of LEDs? Well, first of all, they're extremely efficient. They take very little energy to produce a lot of light. Secondly, they have no filaments or flash lamps. They are solid state diodes, and therefore there's minimum loss of energy through internal heat generation. They can be mounted in large planar arrays like you see across there, which means you can treat large areas of the body in one treatment in a hands-free manner. So they are very therapist non-intensive. You set it up, you start it off, and you can go away and leave your patient to do more important things like make the doctor coffee. And they are comparatively inexpensive. You can get a load of tiny little LEDs for the same cost as you would for one single laser diode. So they bring the cost of the system down for you, which means it's passed on to the patient. And rising healthcare costs are a major problem. So what is the most important target? Well, it is, of course, the skin. And I hope you all enjoyed your lunch. This gentleman here displaying his skin for us very kindly. It is, of course, not inanimate. It is the largest living organ in the human body. It protects the tissue from external insults, and it maintains the homogeneity of the tissue beneath it. But most important for us in phototherapy, it contains all of the target cells for light-emitting diode phototherapy, and at any given time, because of the dermal blood vessels, more than 20% of our body's blood is in the skin. Now, what does that mean? Well, it means that when you give a patient a photofacial, you're not just treating their face. You're actually delivering photoproducts systemically throughout the body. It's a very holistic method of giving somebody a boost. So this explains why, for those of you who have used, for example, the Omnilux, which was the forerunner of the Healite, patients feel great after a session because it's a whole body toning experience, even though you're irradiating only the face, because the blood rushes around the body carrying all these photoproducts that you'll see explained later in the presentation to other areas of the body where they affect, the well-being of your patient. So the skin cells within the skin are one, if not the primary target, one of the primary targets. Let me just remind you a little bit about cellular anatomy. Lovely. Here we have a cell surrounded by its membrane, the cytoplasm, the liquid in the cell, and at the center of the cell we have the nucleus, the heart. And then we have all the bits and pieces that keep the cell going. We have the Golgi complex, which is like an assembly plant. We have the rough endoplasmic reticulum with its ribosomes, which is very important for mRNA, messenger RNA, telling the cell what to do. And then we have the lysosomes, which are the enzyme factories of the cell to keep the cell working in the way it should. But all of this requires energy. So the most important component of the cell for us is the mitochondrion. The mitochondrion produces a wonderful substance called adenosine triphosphate, ATP. ATP is to the cell what Bundaberg rum is to me. No ATP, unhappy cell. No Bundaberg, unhappy Glen. So this is why the mitochondrion is extremely important. And what about the targets then? Well, the main targets in phototherapy are two. Most people will tell you the mitochondrion is the only target. Incorrect. The mitochondria are the targets for visible light, because visible light passes through the cell membrane and is absorbed preferentially in an element in the mitochondrion called cytochrome C oxidase. And that's at the end of the respiratory chain. And this kickstarts the cell into producing ATP. What about the cell membrane? It's a much larger target. And this is the target for IR light, infrared light. Because it's got a longer wavelength, because it's a long wavelength, the cell membrane is the primary target, and this is where the reaction occurs for invisible infrared light, not within the mitochondrion primarily. So visible light passes through the membrane, it's absorbed into the intracellular organelles, in particular the mitochondria, and this starts a photochemical cascade. And this is well known, well proved, well illustrated. Cytochrome C oxidase is activated particularly by 633 nanometer red. ATP synthase produces the ATP, and we get calcium ions and little protons, little packets of energy produced as a result of the ATP synthesis. And these levels in the cytosol, the cytoplasm, activate the cell membrane. So you start to get intra and extracellular exchange. The cell is photoactivated. On the other hand, infrared light stops at the membrane, and it's a photophysical reaction. It literally shakes the molecules in the membrane so that the membrane gets activated first.